This video explores the topic of advanced AI-based measurement systems within the framework of the European project titled Personalized Education in Measurement, Science and Technology Empowered by Machine Learning. Let's begin by understanding what we actually mean when we say AI-based measurement systems. For decades, measurement systems followed a very clear pattern. A sensor collects data, it's amplified, converted, processed, and shown on a display. These systems are reliable and precise, but they operate in a fixed way. Once built and calibrated, they do what they were designed to do, nothing more and nothing less. Today, however, our world produces much more data, and conditions change much faster than before. This is where artificial intelligence steps in. In an AI-based measurement system, the sensors still measure physical quantities, but now the data is interpreted by algorithms that can learn from it. These systems can recognize patterns, adjust themselves when something drifts, and even make predictions about what might happen next. So instead of simply recording numbers, the system begins to understand their meaning. It becomes more than a measuring device. It becomes a smart assistant that learns, adapts, and helps us make better decisions. To better understand where AI fits into measurement science, it helps to look at how measurement systems have evolved over time. The earliest, classical systems were analog, focused entirely on precision through careful calibration and stable hardware. Each measurement was performed manually, often under controlled conditions, and every improvement required human intervention. Then came the digital era, when computers began to automate signal acquisition and processing. Data can now be collected continuously, stored and analyzed, which improves speed and consistency. Still, these systems followed rules written by engineers. They didn't adapt on their own. Today, we're entering the intelligent era, where systems learn from data. AI-based measurement systems don't just record what sensors detect, they interpret, compare, and adapt. They can self-calibrate, detect when something isn't right, and even predict how a system will behave under new conditions. This evolution, from classical to digital to intelligent, marks a major step forward in measurement science. To better understand where AI fits into measurement science, it helps to look at how measurement systems have evolved over time. The earliest, classical systems were analog, focused entirely on precision through careful calibration and stable hardware. Each measurement was performed manually, often under controlled conditions, and every improvement required human intervention. Then came the digital era, when computers began to automate signal acquisition and processing. Data can now be collected continuously, stored and analyzed, which improves speed and consistency. Still, these systems followed rules written by engineers. They didn't adapt on their own. Today, we're entering the intelligent era, where systems learn from data. AI-based measurement systems don't just record what sensors detect, they interpret, compare, and adapt. They can self-calibrate, detect when something isn't right, and even predict how a system will behave under new conditions. This evolution, from classical to digital to intelligent, marks a major step forward in measurement science. Now let's break down the core components of an AI-based measurement system and see what role each one plays. First, we start with the sensors. These are the system's eyes and ears. They measure physical variables such as temperature, pressure, vibration, or voltage, and convert them into electrical signals. Next comes signal conditioning, which ensures those raw signals are clean and reliable. Here, amplification, filtering, and stabilization remove unwanted noise, so that the data truly represents the physical world. The Data Acquisition Unit, or DAQ, digitizes these signals and aligns them in time. This is what allows data from multiple sensors to be processed together accurately. Then comes the intelligent layer, the AI, or machine learning model. This is where the system learns patterns, detects abnormal behavior, compensates for drift, and predicts what might happen next. Finally, there's feedback and adaptation. The system uses what it learns to adjust itself, recalibrate, or alert operators. Over time, every cycle of measurement makes the system more accurate, stable, and adaptive. At the heart of every AI-based measurement system lies the intelligence layer, the part that learns from data and makes sense of what the sensors are observing. Artificial intelligence allows measurement systems to go far beyond collecting numbers. Instead of only recording what is happening, the system starts to understand why it's happening and what might happen next. Using techniques like machine learning, neural networks, and statistical modeling, the AI continuously learns from sensor data. It identifies what normal looks like, detects small deviations that might indicate drift or malfunction, and predicts when maintenance or recalibration will be needed. In dynamic environments, such as industrial plants, smart cities, or medical monitoring systems, this ability to learn and adapt is critical. The result is a measurement system that's not static, but alive, one that improves with experience, refines its accuracy, and supports intelligent decision-making in real time. Now that we know where AI fits in measurement systems, let's look at what makes it truly intelligent, its ability to learn and adapt. In traditional systems, calibration is something engineers perform manually and periodically. But in AI-based systems, the learning happens automatically. Machine learning models are trained using large sets of sensor data collected under different conditions. During training, they discover patterns, how temperature influences pressure readings, or how vibration affects accuracy. Once deployed, the system continues to learn from every new measurement. Each feedback cycle helps the model refine its internal understanding of the process, improving prediction and stability. In other words, the longer the system operates, the smarter it becomes. This continuous learning and self-adaptation are what make modern measurement systems more robust, reliable, and efficient than ever before. Once an AI-based measurement system learns from data, the next step is to use that knowledge for decision and control. In this stage, the system translates its understanding into actions. For example, if the AI detects that a sensor is drifting, it can automatically trigger recalibration. If temperature or pressure readings start to exceed safe limits, it can adjust control parameters or alert operators immediately. These decisions are based on models and confidence levels built over time, meaning the system learns not only what to measure, but when and how to respond. In critical environments, such as aerospace or medical systems, human oversight still plays a key role. The AI acts as a decision support partner, providing recommendations with quantified certainty. The result is a system that doesn't just monitor. It actively maintains performance and prevents errors before they happen. As AI becomes part of measurement systems, one question becomes more important than ever. Can we trust the results? In classical measurement, uncertainty is defined by physics and instrument precision. In AI-based systems, uncertainty also comes from the model itself, from the way it has learned patterns, and from the data it was trained on. A reliable AI system doesn't hide this uncertainty. It quantifies it. By estimating confidence levels and continuously validating outputs with reference measurements, the system earns trust over time. Transparency is the key. Operators must be able to see not only the final value, but also how sure the model is about that value. When uncertainty is measured, documented, and well understood, AI and humans can work together, combining machine precision with human judgment to achieve trustworthy, repeatable results. To truly understand how AI improves measurement systems, we need to start with their foundation, mathematics. Every measurement system is built on a mathematical relationship between what we want to measure and what the sensor actually records. This relationship defines how physical reality is transformed into numbers. In classical measurement, engineers describe that relationship using equations and models derived from physics. The goal has always been the same: to reduce error, remove noise, and make sure our readings represent the real world as accurately as possible. Artificial intelligence extends this same idea, but instead of defining the model ourselves, we allow the system to learn the relationship directly from data. Through concepts rooted in statistics and optimization, AI identifies the patterns that link sensor inputs to real-world outcomes. With each iteration, it adjusts itself to minimize the difference between what is measured and what is true. At its core, AI and measurement is still mathematics, It just uses computation to handle complexity that would be impossible to model by hand. So rather than replacing the math behind measurement systems, AI builds upon it, turning equations into learning processes that adapt, correct, and improve over time. In measurement systems, estimation is core. We try to infer the true state of a system from noisy sensor readings. Classical techniques like the Kalman filter, particle filter, and Bayesian estimators have long been used in control and instrumentation. AI extends this by letting us learn parts of the model, for example, residual correction terms or observation models. Hybrid approaches blend physics models with neural networks. You may keep state space model, but let the network learn nonlinear residuals. This synergy leverages the strengths of both worlds, the interpretability and guarantees of classical estimators, and the flexibility of learned models. Building an AI-based measurement system is only half the job. Verifying that it performs reliably is the real engineering challenge. In classical instrumentation, accuracy and precision are measured with calibration and uncertainty analysis. The same applies in AI systems. Only now we add new layers of evaluation. We still compute error metrics such as mean squared error, root mean squared error, and R-squared to measure how well the model fits the data. But beyond accuracy, we also measure classification performance using precision, recall, and the precision recall AUC, especially when detecting rare events like sensor failures. Perhaps most importantly, AI models must be calibrated. Their confidence should reflect reality. A well-calibrated model not only predicts correctly, but also knows when it might be wrong. This combination of statistical metrics and physical calibration is what ensures that an AI measurement system can be trusted, validated, and safely deployed. As powerful as AI-based measurement systems have become, they also bring new challenges, many of them deeply mathematical and ethical. The first is data quality. AI can only learn from what it sees, so if sensors drift or the environment changes, predictions degrade quickly. Another challenge is non-stationarity. Real-world signals rarely stay consistent. Models must continuously adapt to maintain accuracy. Explainability is an equally big issue. Many neural models work like black boxes, producing correct results but without clear reasoning. For critical measurement tasks, this lack of transparency can be risky. Looking ahead, researchers are building physics-informed neural networks, models that respect physical laws while still learning from data. We're also seeing self-calibrating instruments and digital twins that allow virtual simulation and continuous improvement. The ultimate goal is measurement systems that are not only intelligent, but also reliable, interpretable, and human-aligned. AI algorithms play different roles at different stages of the measurement process. In the filtering stage, neural networks and autoencoders can clean noisy signals, outperforming traditional filters when the noise is complex or nonlinear. During feature extraction, hybrid techniques combine digital signal processing, like FFT or wavelet transforms, with AI models to convert raw signals into structured data. For regression and calibration, classical models such as linear regression are now joined by neural networks that can capture nonlinear sensor behaviors. Fault detection relies heavily on classification algorithms, support vector machines, decision trees, and random forests, which can quickly identify when a sensor is drifting or failing. Finally, in prediction and control, recurrent models like LSTMs and reinforcement learning agents can forecast system behavior and adjust control parameters automatically. Together, these algorithms form the backbone of AI-based measurement from sensing to decision-making. We've now explored how AI works inside a measurement system, but where are these systems actually being used? Artificial intelligence has found its way into nearly every field that relies on accurate data and continuous feedback. In industry, AI helps monitor machines and detect faults before they happen. In transportation, it fuses information from sensors to guide autonomous vehicles. In healthcare, it powers wearable sensors and intelligent diagnostics. It also drives innovation in environmental monitoring and energy systems, ensuring sustainability and efficiency. And in scientific research, AI helps automate experiments and improve precision. In the next few slides, we'll look at each of these areas in more detail and see how AI transforms the way we measure and understand the world around us. Industrial environments are some of the best examples of how AI changes measurement. On a modern factory floor, hundreds of sensors record vibration, temperature, and acoustic data all the time. Instead of waiting for something to fail, AI models continuously analyze these signals to detect early signs of wear or imbalance, a concept known as predictive maintenance. At the same time, AI-based quality control systems inspect every product in real time, identifying subtle deviations that human eyes or traditional algorithms might miss. And through process optimization, these same models learn how machines behave under different conditions, automatically adjusting parameters to save energy, reduce waste, and improve efficiency. The result is a smart, adaptive factory, one that doesn't just measure performance but actively protects and perfects it. The automotive industry is one of the clearest examples of how AI revolutionizes measurement systems. Every modern vehicle, from electric cars to autonomous fleets, relies on a dense network of sensors: radar, LiDAR, ultrasonic, infrared, and cameras. These sensors constantly measure distance, velocity, temperature, and pressure across thousands of components. AI fuses all of these signals into a single, coherent understanding of the vehicle's surroundings and internal health, a process known as sensor fusion. This fusion enables real-time decision-making for braking, steering, and navigation, and it also powers predictive systems that detect mechanical wear or optimize energy use. In this way, AI turns cars into adaptive learning systems, not only reacting to the environment, but continuously improving the safety, comfort, and efficiency of transportation. In healthcare, AI-based measurement systems are redefining how we monitor, diagnose, and protect human health. Wearable sensors, like smartwatches, patches, or implanted monitors, continuously measure heart rate, oxygen levels, movement, and other vital parameters. AI analyzes these streams of data in real time, recognizing deviations that might signal fatigue, illness, or cardiac irregularities, often before the person even feels a symptom. In hospitals, AI supports medical devices that measure imaging, blood flow, or brain activity, helping doctors make faster and more accurate diagnoses. And beyond monitoring, AI enables personalized medicine, adapting measurements and alerts to each patient's unique physiology. In short, AI doesn't just collect health data, it interprets it, providing a bridge between numbers and human well-being. Another vital area where AI-based measurement is making an impact is environmental and energy systems. Sensors distributed across cities, oceans, and power grids continuously collect data on air quality, temperature, humidity, and energy consumption. AI processes these massive data streams in real time, identifying pollution patterns, forecasting energy demand, and optimizing grid performance. In smart cities, AI helps calibrate low-cost environmental sensors, ensuring accurate measurements across large networks. In renewable energy, AI predicts fluctuations in solar or wind output, balancing generation and consumption more efficiently. The result is a cleaner, more reliable, and sustainable ecosystem, where measurement doesn't just observe the environment but helps protect it. We've seen that AI-based measurement systems mark a major evolution from systems that only record to systems that understand and adapt. At their core, these systems are still grounded in mathematics and physics, but AI gives them the ability to learn, to calibrate themselves, and to improve through experience. For engineers, this means our role is changing, from designing every equation by hand to designing systems that can learn those equations themselves. Still, some principles never change. Calibration, uncertainty, trust, and interpretability remain the pillars of measurement science. The future of measurement is not purely digital and not purely intelligent, it's a fusion of both. And that's exactly where the next generation of engineers will make the biggest impact. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Niš and Politecnico di Milano, within the framework of the European project Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.